Hi guys, welcome to your first Chapter 17 video. Chapter 17 focuses on the geometric model, the binomial model. I believe in Chapter 17 you've got a normal approximation to a binomial model. What we're going to start with today is by talking about the geometric model and the binomial model. And when I start this chapter, I'm going to have you guys I'm not going to teach you the calculator shortcuts to solve some of these problems, and I really want you guys to not explore for yourselves just yet some of the calculator opportunities that are out there to solve with the geometric and the binomial. We'll get to those. When we get to those, I'll be fine with you guys using them indefinitely. But I think it's important that we first play with this computationally, make sure that we understand how these two equations I'll present to you work before we fly forward with the technology we have. So to begin, we've got to introduce what's a Bernoulli trial. And Bernoulli trial is just a special type of random outcome, or a random occurrence, I should say. It's not an outcome, it's an occurrence that, I want to keep the current color scheme. It has the following three characteristics. So exactly two outcomes. This could be, think of a test. If someone goes into a multiple choice test, doesn't know a thing, they just answer every question randomly, and they're just looking to pass. Well, that has two outcomes. There's the pass-fail. Probability of success is independent for your Bernoulli trials, and we're going to really, I don't think the test example holds for parts 2 and 3. We'll look at a few examples down below to further clarify this Bernoulli trial. It's got these three conditions: two outcomes, always two, never fewer, never more. Independent probability of success, so success or failure in a subsequent trial doesn't affect future trials. And then third, the probability of success is the same on each trial, and the probability of failure, which we denote Q, is also the same. So P is for success, Q is for failure. And what we're going to do is, just to make sure that we understand what a Bernoulli trial looks like, for 1 through 4 here, let's determine if it is Bernoulli. Well, rolling a 1 on a die, okay, doesn't meet the conditions. Notice I'm just saying rolling a 1 on a die. I'm not talking about the number of dots that come up on a single die. So we actually only care about two things. Did we roll a 1 or not? So yeah, for the first piece, this has two outcomes. That condition is met. For the second piece, independent probability of success, sure, you roll a die a single time. Whether or not it comes up a 1 or a non-1, which would be 2 through 6, doesn't affect future rolls. So the independent probabilities hold. And then the last thing that has to be met is that the probability of success is a constant. Well, P is equal to 1/6 here, because it's one of the 6 sides of the die. Q would be equal to the complement, or 5/6. So sure, this is a Bernoulli trial. Okay. Second example, flipping a coin. Well, it's got two outcomes, heads or tails. So that condition of two outcomes is met. We need independent probabilities of success. Sure, same deal as with the rolling a 1 on a die. Whether or not you get a head or a tail on the previous flip doesn't determine what's going to happen on the current flip. So you've got independent probabilities. That condition's again met. And then, why am I doing 1, 2? I did A, B. Let's do A, B, and then C. So the probability of success, it all depends upon how you're defining success in the problem you're working on. But it's either 50% for heads or 50% for tails. Q, again, is a complement. So you have, again, a Bernoulli trial. Let's get that I in there. Okay. On to the third piece here. Drawing an ace from a deck of 52 cards. Well, first of all, in terms of the outcomes, yeah, this is met. It's a little bit, you can conceptualize it like the first example here. You either draw an ace or you don't draw an ace. That's all that they seem to care about in this in this instance. So we do have two outcomes, ace or non-ace. B, do we have independent probabilities? Well, that depends upon whether or not we're replacing the card that we're drawing. They don't mention that we're replacing the card, so it looks like we do not have independence. Okay, that is to say that you drawing perhaps an ace in the first draw from these 52 cards, well, that leaves you with 3 aces remaining in the deck, which now has 51 cards, so you have changed the probability. So it's not independent. The probability of success does depend on a subsequent draw. And then lastly, that also influences the probability of success or failure. P is not constant. Okay, so this would not be a Bernoulli trial. Just abbreviate, not Bernoulli with NB. Value of a die roll. Well, in our first example, we said rolling a 1 on a die. That's what we cared to follow. Here, the value of a die roll, that can occur 6 different ways. So that would leave us with, for the first of the 3 conditions, there are 6 outcomes. We know automatically that it's not Bernoulli. These are independent trials, though. The value of a single die roll won't affect the value of the next. And P and Q don't make sense to talk about in this case because P and Q are just 2 probabilities for 2 outcomes, and A, with that condition, was already not met. So this doesn't make sense. Don't follow. Okay, so this would also be not Bernoulli. Okay, the reason that we spend time talking about Bernoulli trials is, again, just that the 2 models we're going to look at, the geometric and the binomial, both depend upon that being the specific type of random event that occurs. 2 trials, independence, constant probability of success, and therefore of failure. Okay, so here's your first of the 2. Tends to be the easier to work with, the easier to memorize, but also because it's the easier to work with and the easier to memorize, it winds up being a little bit less useful. The binomial model, I think, is the cooler model of the 2. So what you have represented here is the probability model in a tree, or not in a tree, excuse me, in a table. And then also, this guy right here is the important equation. And we're going to explain how this works. So if a Bernoulli trial is one that has 2 outcomes, either success or failure, which we'll denote with P and Q here, and the trials are independent, well, branching off of my first success, I could either have success times success. That'd be one of the ways that these random events could occur. Or I could have success followed by failure. I could have an initial failure, which you see right here, followed by success. So QP or QQ, okay, et cetera, et cetera. And you can just continue to branch off. Well, within this tree that extends further, I mean, you can do this an infinite number of times and keep talking about, okay, what's the probability that in like 5,000 coin flips I've got success, failure, blah, 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 blah. Just go down the line. Okay, so hence the dotted lines. You can repeat this over and over again ad infinitum. So the geometric model says, let's just keep track of the number of trials until we have a success. So if you're talking about a coin flip, maybe you've defined P to be, yeah, sure, the probability of success. Maybe in this particular case, P is the probability, P is equal to the probability of a head on a coin flip. Okay? And maybe Q is equal to the probability of a tail then, okay? So the Bernoulli model in this case would say, okay, what's the probability that you get your success, you get your head on the first coin flip? Or what's the probability that you don't see your first success until the second coin flip? Or what's the probability that you don't see your first success, all these P's, until your third coin flip, or fourth, or fifth? Okay, moving on down the line. Well, where these numbers come from in the second row, you can kind of see, at least a sliver of it, from the probability tree below. So the probability that you would see a success on the first coin flip is just P, okay? That's the first outcome we would want to keep track of. Well, if this geometric model is keeping track of how many coin flips you need or Bernoulli trials you need until you see your first success, the next one could come after you go failure followed by success, okay? There's your Q times P. And then if you're going to have 3 coin flips or 3 Bernoulli trials before you see your first success, that would be Q, 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 then Q, Q, P, okay? Failure, failure, then success. All right, so to have the probability of any given number of Bernoulli, let's see, let me back up. For X to be the number of Bernoulli trials that you need before you see your first success, you're going to have Q minus that number. In this case, this is Q to the 1 minus 1, or 0, failures preceding it, okay? So we have Q to the 2 minus 1, failures preceding our first success. We've got Q to the 3 minus 1, or 2, failures preceding our first success. And then we go 4 minus 1 is your 3, okay? So there's sort of the meaning behind your geometric model here. And we've got this handy equation. You don't have to draw out a probability table like you've done in the past to work with your geometric model. You can just use this equation, which is circled in red up here. Okay, that's your Q to the X minus 1 times P. Okay, so the expected value and the standard deviation of this I'll give to you. The expected value is there's a derivation of that on the 3rd page of this chapter 17 from your book. Expected value winds up being 1 over P, and the standard deviation of the number of trials until you would see your first success is Q over P squared. Okay? Note that those are not on your stats reference sheet, as are the mean and standard deviation formulas that you'll need for the binomial formula. Okay, so 1 over P and the square root of Q over P squared, those you'll need to commit to memory. Okay, let's see how this works in practice. So only about 60% or 6% of people have O negative blood, which is also known as, let me jump forward here. What do we call that? Universal. That is a universal blood type. Okay. Only 6% of people have O negative blood. If donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O negative blood? Well, we'll stop there and answer our first question. So if X is equal to the number of donors till O negative, okay, well, let's talk about, we know that we can use a geometric model here because you have Bernoulli trials, all right? You've got 2 outcomes. Either someone has O negative blood or they don't. Secondly, these are independent events. Someone having O negative blood in the first case doesn't affect whether or not the second person has O negative blood. I mean, I guess technically that may not be a fair assumption because people might travel in families, in which case families tend to have similar blood types, but we're gonna skip those details, okay? So we'll assume that they're independent events, and finally, the probability of success is constant. Okay, 6% of people have this O negative blood type. Well, so we've defined our variable, we've defined what X means to us. Let's talk about P being the probability of success, which is 0.06, and Q the probability of failure, then the complement would be 94%. Okay? So we want the expected value of X, which, according to last slide, was just 1 over the probability of success, which would be, in this case, 1 over 0.06, which comes out to be, I believe, 16.7, which is approximately 17 people that you would expect to go through until on that 17th person, on average, you would have your first person with O negative blood. So that means you had 16 failures preceding it, okay? So second piece that they want here is what's the probability that the first O-negative donor is found among the first 4 people in line? So in B, first O-negative donor is found among the first 4 people in line. They want the probability of the following. You don't have to introduce a new variable. They want the probability that your success occurs on the first person, the probability that success occurs on the second, the third, and of the fourth, all added up. Okay, so you can just use the geometric model here 4 times, which it's really not that cumbersome because we know Q is 94%, we know P is 6%. Well, if you have your first success, your first O-negative blood type on that first donor try, that random donor, then that would just be 0.06. Okay, you had no failures preceding it. Okay. Then if the probability of success, your first success being the second person would be, well, that's 1 failure times your single success. The probability that your third trial would be your first success would be 2 failures, 0.94 squared times 0.06. And then the probability of success being your fourth, well, that is, let me make sure I'm getting my addition signs in here. 3 failures, 0.94 to the third times 0.06. Simplify this out, and you find, I believe, 0.2193. It's the probability that one of your first 4 people will, oh, that's too big. That's too big. Let me see if I can correct that real quick. For some reason I was putting 0.96 instead of 0.94, 0.06 plus 0.94 times 0.06 times 0.06, come on calculator, plus 0.94 squared times 0.06 plus 0.94 to the third times 0.06. Well, it's about the same. It's about the same. It's pretty close to that. Okay, so that's again the probability of one of the first 4 people having your first success. So what did we just find here? Well, let's go back to a familiar tool. Let's go back to the probability tree real quick, and I'll draw this out to represent what we just did. So for each person, we either had O-negative blood or you didn't. So I'll do O complement. Okay, so the probability of O-negative on the first case, that was P. Of us not finding what we wanted, that was Q, okay, 0.94. Well, if you hit your O-negative blood on the first case, you're done. You don't need to do any more. Then you're looking for, on the second case, did we hit O-negative blood or didn't we? O complement. Okay, so if you did hit O-negative blood, you did 1 failure times a success to get to that that particular case. Or if you didn't hit O-negative, or O-negative blood again, you did Q times Q. Okay. Well, there again, you can stop after that second case because you finally hit your first success for this Bernoulli trial. And then in the third draw of a donor, you either again got the O-negative blood or you don't. So you're looking at Q squared times P, which would be what you care about, or let's do this in red to denote there's a difference in the meaning here. 3 failures, Q to the third. Okay? And then finally you've got your O-negative blood being the fourth draw, or you've once again not found O-negative blood. So you're either looking at 3 failures, then success, or 4 consecutive failures from which you would branch off yet again. And all of these circled probabilities build into answering part B. Okay, all right, so there's the geometric model played around with a little bit. You guys are going to do that some more in class. The binomial model is more powerful. Whereas the geometric model says, what's the probability that our first success occurs on the xth trial, where x could be 1, 2, 3, 4, 500, etc., etc. The binomial model says, if I have n trials, let's say I do 5 flips of a coin, okay? So if n is equal to 5 flips, let's look at this in an example. 5 flips. And P is the probability of a head on a coin flip, which we know is equal to, I don't put that in parentheses, which is equal to 0.5, okay? Then X would be the number of successes in n trials. X could be, okay, X could be 1, 2, 3, 4, or 5, okay? So you could, excuse me, I missed one on the low end. You could have 0 head flips as well, okay? So it's a more powerful tool. It says if we've got some set number, some n number of trials, and we've got a constant probability of success, because these are still Bernoulli trials, how many successes do we have out of that number? That's cool, and it's powerful. This probability model is broken into 2 pieces. There's a combinatorics piece, which is your n choose x, and we're going to see where that comes from here shortly. And then this piece, p to the x times q to the n minus x, that we'll explain in context below here. So there's 2 pieces. This is your combinatorics piece, and this is really your probability piece. And the probability piece is the simpler of the 2. Your expected value, or the mean here, this is on your stats reference sheet, but it is n times p, the standard deviation of the number of successes in n trials is the square root of the number of successes times your probability of success times your probability of failure. All right, so again, we said that we would come back to the combination parentheses, the combinatorics element of the binomial model. The success-failure product, though, let's look at that with an example. So let's talk about the case where we have let's say I want to find, let's use everything that we wrote in red up above. So for 5 flips of a coin, we've got the probability of success of a head is 0.5. And the values we could take on would be 0 through 5. Let's talk about when the probability that the number of successes we have is equal to 2. Okay? Well, you can visualize your 5 coin flips this way. 1, 2, 3, 4, 5. You could have head followed by 3 tails. Okay, there's one way that this could occur. You could have head, tail, 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 head, and that would be another way that you're still hitting the 2 successes out of the 5. And so there are all these different ways. You could do this again, obviously, for the sake of demonstration. You could talk about when you've got head, tail, tail. So what you can see here, the common theme is that to make sure that you're having 2 successes specifically out of 5 flips of a coin, you know that somewhere along the lines you've got a probability of success times a failure times another success times a failure times another failure. Okay? So this would be one way 2 successes could occur. But as you just saw, it's certainly not the only way that 2 successes could occur. Okay? So that's what the probability piece right here finds. That's the probability of a single successful case, if you want to think of it that way. That you have, and I should be a little bit clearer, not successful case, but in this instance it would be what we're circling in red right now will tell you how you can find 2 successes out of 5 Bernoulli trials one time. But it doesn't capture the whole essence of the problem, because that can occur multiple ways. You can rearrange the heads and the tails here. Okay, So, for instance, let's use these numbers. If we want to find the probability that x is equal to 2, ignoring this n choose x for now. We're going to explain this a little bit more next slide. That would be times the probability of, well, the probability of a head is 0.50 to the x, which I'm circling right now. That's just the number of successes you want to see. So 0.50 to the second, your 2 successes, times the probability of failure, which is the complement, 50% chance of tails, to the n minus x. That's to the 5 outcomes, 5 Bernoulli trials, minus the 2 successes, which just kind of winds up being 3. Okay? So you'll always have a number of trials or successes and a number of failures equal to the number of trials in all. N was equal to 5 here. We had 5 flips of the coin. Okay, so there is the first piece of the binomial formula, circled in red. The second piece that we need is this combinatorics piece, and to get that, we first need to understand a factorial. A factorial is defined as follows. If I have d factorial, what I'm saying is that is d times d minus 1 times d minus 2, onwards and onwards down the line down to 2 times 1. Okay? So if I took 5 factorial, that would be 5 times 4 times 3 times 2 times 1. Okay? So there's a factorial. It's relatively simple enough to understand. It uses that exclamation mark it's really an abbreviation of 5 times the preceding number times the preceding number on down to 1. Okay? So let's try to make an attempt at understanding this combinatorics piece in red here. Okay, so as a summary, the probability piece tells us what's the probability that we see our x successes and n trials a single time. This combinatorics piece is going to fix the fact that that can happen multiple ways. Okay? So what you see here on this next slide is 5 factorial written out all 120 times. Okay? That is your numerator here for this combinatorics piece. 5 times 4 times 3 times 2 times 1. It's showing you that you can have, for instance, 1, 2, 3, 4, 5 in the upper left. You could rearrange to be 1, 2, 3, 5, 4. So every row is a unique combination of ordered 1 through 5. Okay? So but clearly that doesn't fix the number of ways we can get heads and tails. That's way too many ways. Surely you can't have 120 different combinations of 2 heads and 5 flips of a coin. That doesn't make sense. That's where this 5 and the 2 are coming from. On 5 flips of a coin, how many different ways can we choose 2 of those flips to be successes? Okay? So here's the numerator, the 5 times 4 times 3 times 2 times 1. But the denominator divides some stuff out. In blue, what it's dividing out are all the ways we don't care about the arrangement of the other 3 numbers. So in red, let's check out what we have in red for everything right here. You could have your 2 successes be the first case and the second case. That's why they're highlighted in red. But this numerator of 5 times 4 times 3 times 2 times 1 cares about the 3, 4, 5 combination, the 3, 5, 4 combination, the 4, 3, 5 combination, the 4, 5, 3, etc. We don't. We just want to know in what numbers would represent our successes. So that's just the 1 and the 2. So in blue here, notice that's 6 rows in every honeycomb piece. All right? Well, the 6 is coming from the fact that if I've chosen 1 and 2 to be my successes in red, there are 3 numbers times 2 numbers times 1 number that are left to fill those other 3 positions. Okay? So this 3 factorial that you see here, which is represented as 3 times 2 times 1 in your denominator, is dividing out the redundancy. Okay? And then secondly, there's a separate piece here. Well, if the factorial gives us this way of ordering all 120 different ways you could choose 5 numbers in a row, there's redundancy in the fact that you could say you choose the first number to be the first flip of a coin to be a success, then the second flip of a coin to be a success, versus the second flip to be your first success and the first flip to be your second success. Okay, so this 2 times this division by 2 here is dividing out all the ways in which you've got 1, 2 versus 2, 1. Well, they're both successes, so we don't need to repeat those. Same thing with, let's see, where is this? 1, 4 and 4, 1. We're dividing out these 2 ways that you're still just defining successes in these 5 trials. So there's a little bit on the combinatorics piece. So it finds all the ways in which you would have, you could have, in 5 flips of a coin, 2 of those 5 flips be successes. So what would this come out to be, simplifying this? Well, divide the 3s, 2s, and 1s out, and you're left with 20 up top over 2. So there are 10 different ways that you could have 2 of the 5 flips be successes. All right, let's go to what we're going to do next. Now, just to clarify, what we showed in the last slide, that is not essential to you being able to do the problems that are coming up with the binomial model. All right? What you do need to be able to work with is just the probability of x equal to some lowercase x equals, and choose x, times p to the x, q to the n minus x. That equation you'll need to plug into. So let's do that here. Suppose 20 donors come to the blood drive. What are the mean and standard deviation of the number of universal donors among them? Okay, so we just need to find the expected value if we have a binomial model here, and the expected value, and I want to write that. Let's just do binomial. I'm going to find the expected value and the standard deviation here. Well, okay, so these are Bernoulli. You've got 20 donors, none of whom affect the probability of seeing that universal blood, which is 6% likelihood for any random person. So the mean of this binomial, expected value of x, is equal to, going back here, I think it was n times p, yep, right in the middle. The number of trials that we have, well, we have 20 trials, times the probability of success, we said was 6%. So this comes out to be 1.20. Okay, we expect to see about, which is approximately one person to have this O negative blood type among the 20 people coming to the blood drive. Well, let's find the standard deviation next. Standard deviation of x here is equal to the square root of npq, which is equal to the square root of 20 times 6% likelihood, 94% likelihood of failure, which simplifies to, calculate this real quick, square root of 20 times 0.06 times 0.14 is 1.06. Okay, so there's an average variation of about 1 person in this blood drive scenario where you have 20 people coming in at random. Okay, so we've answered this first piece, which I'll star at the end of that question. Then they want, what's the probability that there are 2 or 3 universal donors? Okay, so using our binomial model, what's the probability that x is equal to 2 plus the probability that x is equal to 3? Well, why don't we answer this by solving each chunk? Probability that x is equal to 2 is equal to, well, there are 20 donors in all. That's your n value. And we're choosing 2 here to be our successes. okay, times the probability of success we know is 6% to the second, because we've only got 2 people with that blood type, so that would leave 94% to the 18th. There were 18 failures, so to speak. Okay, so this simplifies as follows. The 20 choose 2, from the last slide you kind of saw how that worked. We do the 20 factorial, okay, over 2 factorial times 18 factorial. It's always, you're always going to have the number on bottom in your denominator with the factorial following it, and then the difference between your 20 and your 2 in this case following the 2 factorial, okay, times your 0.06 squared times 0.94 to the 18th. So this is, well, 20 times 19 times 18, and then you could keep going times 17 times 16 times 15, etc. But it's 20 times 19 times 18 factorial over 2 factorial, 18 factorial. Well, you see the same thing on top and on bottom, so let's cancel that out. Well, 2 factorial is just 2 times 1. Okay, so this is really simplifying further. 2 times 1 is just 2. Divide that with the 20, and you've got 10 times 19. Okay, 10 times 19 up top. Nothing is left on bottom except for the obligatory 1. Okay, and then this 0.06 squared times 0.94 to the 18th. Okay, so the probability that of 20 people you have 2 that have this O negative blood type would be, let's do 0.06 squared times 0.94 to the 18th, and I find, so this is 10 times 19 times 0.00118. Okay, so 0.00118 times 190, that probability of success is 22.4%. Okay, so there's just that we see 2 O negative blood donors. So this chunk goes right in there, and we'll get our final answer here in just a second. Okay, so let's use this binomial formula one more time for when x is equal to 3. Well, we have 20 blood donors. We're taking 3 to be our successes. So p is to the 3rd power, which, let's see how I wrote that. Okay, just wrote your probability of success is 6% to the 3rd power. Your probability of failure is 94% to the 17th power. So this is breaking down this combinatorics piece. That's 20 factorial over 3 factorial, 17 factorial, times 0.06 to the 3rd, 0.94 to the 17th. Well, let's write this 20 factorial, if it's 20 times 19 times 18 times 17, etc., as 20 times 19 times 18 times 17 factorial. So that cancels with the 17 factorial on bottom. 3 factorial is 3 times 2 times 1. 3 times 2 times 1. Well, that comes out to be 6. So why don't we do some cancellation here. The 6 can cancel with the 18 to give us 20 times 19 times 3 up top. Okay? So we're almost there. We have 20 times 19 times 3 times 0.06 to the 3rd times 0.94 to the 17th. And I see in all this is a 0.0860, so an 8.6% chance that you would have 3 universal blood types of your 20 donors. Okay, so in all, you've got 22.4% plus 8.6%, which gives you a 31.2% chance of seeing 2 or 3 O negative blood types among your 20 donors. So the binomial formula is powerful. This right here, all of this, again, I wouldn't focus on that too much. If that's confusing, lay off. You don't have to have a strong understanding of that to get through the rest of the class. Just trying to give some background there.